All right, welcome back, folks. So I hope you are enjoying this journey so far, and we're going to get into really crazy concepts in complex numbers. But in order to do this, we're going to get into some, I'll call it review in calculus, and we're going to be talking about sequences and series in the complex numbers. So, uh, just real quick, so the content, it will be similar, analogous to sequences and series. And uh, in Calc 2, right? In Calc 2, where they talk about sequences and series. So let's discuss about what a sequence is in terms of the complex numbers. Okay. So a complex sequence, z sub n, right? It looks like this, is a function. I'll call it u. And it maps to numbers in the natural numbers to complex numbers. So this n represents the set of natural numbers. So positive integers, 1, 2, 3, 4, 5, and so on. This here's the set of complex numbers. We've seen that before. Okay. All right. So an example of a complex sequence may look something like this: 1 plus I to the n power. I is the square root of -1, right? So if I list out these the terms of this sequence, well, when n is 1, we'll have 1 plus I. When n is 2, we'll have 1 plus I squared, right? When n is 3, this is 1 plus I cubed. When n is 4, we'll have 1 plus I to the fourth, right? And this pattern keeps going, right? Okay, so this is n is 1, n is 2, n is 3, and then n is 4, right? Okay, so you get the idea, right? Now the question is, when does a sequence converge or diverge, right? So if this is write out remark here, if the limit as n goes to infinity of z sub n equals to L, if L is equal to a complex number, let's say a plus ib, right? We say that the sequence, shoot, let me draw that a little bit better. Z sub n is convergent. Convergent. Or they say converges to L, right? Otherwise, the sequence Z sub n diverges. Okay, otherwise Z sub n diverges. Okay, so here's an equivalent test to show a sequence converges. So a sequence z sub n converges to L, which could equal to A plus IB, if and only if the limit as n goes to infinity of the real component of the sequence z sub n. So look at the real real number values in the complex sequence. It converges to A, and the limit as n goes to infinity of the imaginary component of the complex sequence z sub n converges to B. Okay, so that's just another test to show that a sequence converges. Okay, so let's look at an example. So here's an example. So here's an example. Determine if, oh shoot, this sequence, 3n times I plus 2 divided by n plus n times I converges or diverges. Okay, now I want you to pause this video and think about how we would show either this sequence here converges or diverges. Okay, so pause the video and I want you to work on this example. Okay, so I assumed you worked on this example. Let's see if the sequence converges or diverges. All right, so I'm going to use this. So the complex number, I should say the sequence of complex numbers, right? It looks like this. And over n plus n times I in the denominator, right? So we want to write out this quantity in terms of, let's say, A plus BI form, right? The real and imaginary components. So what we're going to do is we're going to multiply the numerator and denominator by the complex conjugate of the denominator, right? So n minus n times I. N times I right here. Okay. And so this should equal to, so we'll have n squared minus n squared I squared. That's another plus n squared. And the numerator will have 3n squared times I. We'll have a plus 3n squared from those two terms there. And we'll have plus 2n. It'll be these inside terms. And then the last terms here would be minus 2n times I. Okay. And so this would equal to the real component would be 3n squared plus 2n. So 3n squared plus 2n divided by n squared, 2n squared. 2n squared. And then the imaginary components will be those values divided by the denominator here, right? So, so we'll have plus I times 3n squared minus 2n over 2n squared. Okay? So the sequence z sub n, right, it will equal to the sequence with the real and imaginary components being listed like these respectively, right? So Now we have to do is show whether the real part converges and the imaginary component converges, which it does, right? The limit as n goes to infinity of 3n squared plus 2n over 2n squared. This is a rational function here, right? So not only that, the exponent, the leading exponent on n is the same, right? So in this case, this equals to the ratio of the leading coefficients, which is 3/2. Okay, 3/2. Likewise with the imaginary component, right? Likewise with the imaginary component, we have 3n squared minus 2n over 2n squared. This will also equal to 3/2, since the highest exponent is the same on the numerator and the denominator, right? So this here, this will also equal to 3/2. So the limit as a whole, so the limit as n goes to infinity of z sub n equals to 3/2 plus 3/2 I. Okay, so that's pretty straightforward. Okay, so let's look at what a series is. So series is a sum of terms. It's a sum of terms, complex numbers. So it looks like this. Z1 plus Z2 plus Z3 plus Zn plus yada, 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 right? So it's a sum of it's a sum of terms, sum of complex terms, right? And a series converges if S sub n converges, where S sub n equals to the sum from k equals 1 to n of z sub k. And then term by term, this equals to z1 plus z2 plus z3 all the way up to z sub n. Okay, so the series will converge if the terms of the sequence S sub n, where it's represented as this sum, converges. This here is what's called the sequence of partial sums. The sequence of partial sums. Okay. Okay. So this will converge to a complex number, right? So there's many series and sequences you've worked with in the real number sense. But the tests for series that you've seen in Calc 2, it will be similar to so the methods for showing convergence in the complex numbers will be the same for showing convergence in the real numbers. Okay. Algebraically speaking, geometrically, it's going to be a little bit different. Okay. So the first series I want to look at is what's called a geometric series. This is one of the first type of series you have worked with in calculus, right? So so a geometric series may look something like this. right? And this equals to a plus az squared plus all the way down to azn minus 1, and this keeps going, right? So this is a geometric series, and to figure out where it converges, where a geometric series converges, well, let's suppose we define the sequence of partial sums as a plus az plus az squared on up to the nth term, which is a times z the n minus 1. Okay. All right, so that's the sequence of partial sums. So I'm going to call this equation 1. And if I multiply both sides of this equation by z, I'll get the second equation. So z times s of n is equals to a times z plus a times z squared all the way up to a times z to the n. Okay. If I subtract the first from the second equation, what's going to happen is we'll have terms that will cancel. So the az up here will cancel with this az down here, right? So these will cancel. The az squared term will cancel. The a times z squared terms in the first and the second equations will cancel. On up to this term, this will cancel with the a times z, the n minus 1 term down here. And we are left with two terms, this constant a and this term, a times z to the n. So this will be a minus a times z to the n. So I'm going to write out what this equation reduces down to. So we'll have s of n minus z times s of n equals to a minus a times z to the n. So if we solve for s of n in this equation, we'll have the sequence of partial sums for a geometric series. So a sequence of partial sums for a geometric series would be a minus a times z to the n minus 1 divided by 1 minus z. Okay. Or if you just factor out the a's, we can express this is z to the n, excuse me, z to the n over 1 minus z. So this is the sequence of partial sums for a geometric series. Would you know when a geometric series converges? It's exactly what you would expect. If we look at the modulus of z, right? If this modulus of z is less than 1, okay? If it's less than 1, then the geometric series converges. And it converges to a real number, to a complex number, excuse me. A is a complex number. So the length of z is less than 1. So z to the n, this power, will eventually be closer to 0 plus 0i, right? So so your partial sum for the geometric series would equal to a divided by 1 minus z. 1 minus z. Okay. If the modulus of z is greater than 1, right? The series diverges. The geometric series diverges. the length of z can't equal 1, right? So these are the two cases, right? If the length of z is less than 1, then it converges to this real number. And if the length of z is bigger than 1, your series will diverge. Okay? Some examples of a geometric series in the complex numbers will look something like this. Here's one example. 1 plus c plus z squared plus z cubed plus z sub n. Here's an example of a recognizable geometric series. Okay, so a usually is the first term, right? A is usually the first term in the geometric series, and then z is the common ratio, right? Okay, so in this case, this series will equal to 1 divided by 1 minus z. Okay, the common ratio is z. And the length of z has to be less than 1, okay, in order for this to converge. Here's another one. 1 minus z plus z squared minus z cubed plus. How would you figure out the nth term? Well, on the one hand, the signs are alternating, right, for each term. Okay. And then you're just increasing the power on z by 1. So the nth term would be minus 1 to the n times z to the n, right? And so this would converge to, or you can write out minus z to the n. That's just another way to express that, right? So the first term in this case is 1, but the common ratio is minus z. So it'll be 1 minus negative z, which is equal to 1 over 1 plus z. And this is once again converges if the length of z is 1. Okay. So, okay. Those are pretty recognizable geometric series. Here's an example. Let me organize this. Show if this sum k equals to 0. Three times 2 over 1 plus 2i to the k converges or diverges. Now I want you to work on this example, okay? So pause the video and see what you come up with. All right, so I assumed you worked on this example. Let's work out and see what this, if this series converges or not. Okay, so the common ratio, here is 2 over 1 plus 2i, right? So 2 over 1 plus 2i. So I'm going to write this out in a plus bi form. And so we're going to have to multiply the numerator and the denominator by the complex conjugate of the bottom number. And so this will equal to 2 minus 4i. And that would be divided by 1 plus 4 minus 4i squared, so 1 plus 4. And so this equals to 2/5 minus 4/5 I. Okay. And we know that the length of this common ratio here is less than 1, since the real and imaginary components, their ratios is less than 1, right? So the length of z, if you want to do the brute force way, right, this is 2/5 squared plus minus 4/5 squared. right? So this is equal to 4 plus 16 over 25, which is equal to radical 20 25ths or 4/5. Okay. Which is 2 over root 5. Okay. So this here is less than 1, right? The length is less than 1. So we know that this series converges, but since it's a geometric series, this will converge to 3 times the first term. So in this case, it would be 1 over 1 minus the common ratio. So in this case, it's 2/5 minus 4/5 I. That would be the common ratio. All right. So we're going to have to simplify this answer. Simplify this quantity, and we'll have 3 times 1 over 3/5 plus 4/5 I. And so that would be equal to 3 over so 3/5 minus 4/5 I. And so this is oh shoot. Okay. So 3/5 plus 4/5 I times 3/5 minus 4/5 I. And so that would equal to 9/5 minus 12/5 I. Divided by some minus 7/25. That's what you should get on the bottom number, and that is where the sequence or the series would converge to. Okay, 9/5 minus 12/5 I divided by negative 7/25. Okay, so what I'm going to talk about next is how we can test for convergence. Or I should say tests to show convergence, right? One of them is using the nth term test. And it goes like this. This is the nth term test, or they say the test for divergence. If the limit as n goes to infinity of z sub n, if that does not equal to 0, 0 plus 0 I, then we can say that the series of a sub k diverges. Okay? This is what's called the nth term test for divergence. Okay? There's a problem in your homework in your problem set, which says that what can we say if the limit of the modulus of z sub n equals to 0, I believe, right? If that equals to 0, what can we say about the convergence or divergence about this, right? So I want you to think about that for as we move forward here. Okay. The second one is these tests have to do with absolute convergence or divergence. Okay. So the series of z sub k converges absolutely if the series of the absolute value of z sub k converges. All right. And then absolute convergence implies convergence. Okay. The third one is the series of z sub k converges conditionally if the sum of the absolute value of z sub k diverges, but if you show that the series of z sub k converges. All right. In the real numbers, can you think of an example of a series that would look like this? Well, one example could be one example that you have seen in the real numbers is something like this, right? This is what's called the alternating harmonic series, right? And what about an example in the real numbers that talks about number two, right? An example of a sequence like that would be minus 1 to the n over n squared. This here is an absolute convergence series, right? Okay. N squared, that would talk about a p series, right? P series, it deals with the exponent number if you're dealing with a series in K, right? Or N. So let me write out first what a P series is. So in the real numbers, so a P series, 1 over K to the P, it looks like this, right? So this series converges if the exponent number P is bigger than 1, and this series would diverge if the exponent number P is less than or equal to 1, right? So this deals with an application of a test for series in the real numbers called the integral test, right? So the last one, actually, those are it. Okay. So these are the different tests for series that you'll see in the context of complex numbers, right? So the test for divergence, the nth term test, this is absolute convergence, this is conditional convergence, and sometimes you'll see problem sets where you'll recognize what a p-series is in terms of the real numbers, okay? And there's going to be two other tests that I want to write down, and it will be similar to what you've seen in calculus 2. And those tests are the ratio test and the root test. So the ratio test looks at the limit as n goes to infinity of the ratio of two terms in the series of z sub k, right? So if we suppose this limit equals to L, and we'll see where this series will converge regarding to what this value L equals to, right? So if this L value is less than 1, the series converges. Absolutely. So the series converges if L is bigger than 1, the series diverges. And if L equals 1, the test is inconclusive. Okay. You might be dealing with an example of a ratio of a rational function, right? And something like a rational function would not work using the ratio test, because you'll get the ratio of the two terms, which are rational functions. You'll get that ratio equal to 1. So, like, if you were to do the ratio test, let's say n squared plus 2n plus 5 over n cubed plus 4n plus 6, let's say. Okay, in the real numbers. And if you do the ratio test, you'll get that this is equal to 1, right? That's why we say that test is inconclusive. So that third part only deals with rational functions in your series, okay? So the same test would, well, I'll also say the last test that I'll write out is the root test. The root test, okay? And this looks at the limit as n goes to infinity of the nth root of the absolute value of z sub n. And if this equals to L, let's say, right? Okay. If L is less than 1, the series converges. If L is bigger than 1, the series diverges. And if L equals 1, the test is inconclusive. Okay, the test is inconclusive. All right. So, there's also a different type of series that we're going to look at in the next section. And those are what are called power series. Okay, so power series. It looks like this. This is going to be a lot. So, yeah, this chapter, chapter 6 in the book has quite a lot of content. So, yeah, there's a reason why this video is going to be so definition heavy. So, we'll have extra time to look at examples and formulate series and all that goodness. So this is what a power series looks like. So we'll have a center of a power series, and it's at Z naught, and we'll have a radius of convergence. So we'll have a radius of convergence. So as you recall, in single variable calculus, the radius of convergence would be a distance on the number line, right? And then Z naught as the center will be a point on that number line. And we had what was called an interval of convergence, right? Right, the interval of convergence, and the radius of convergence is just the distance that you have to go away from Z naught. Okay. So this time around, we're going to be dealing with a R neighborhood. So if I have Z naught in the complex plane, so the radius of convergence would be R, let's say, but it's not an interval of convergence anymore. It's going to be called a circle of convergence. That interval is a circle of convergence. Okay. So it's called a circle of convergence. And it will be points on or possibly on the bound. So it'll be points inside and possibly on the unit circle that will cause the power series to converge. So the circle of convergence would be the length of Z minus Z naught is less than or equal to R. Okay. So we'll have a circle of convergence. Okay. So to determine the radius of convergence always use the ratio test. Okay. If the limit as n goes to infinity of capital A sub n plus 1 divided by A sub n equals L, right? A sub n plus 1 over A sub n, those refer to the coefficients of the power series, right? A sub k here. A sub k. And if this L value is not 0, okay, if it's not 0, then the radius of convergence would equal to 1 over L, right? If on the other hand, if you have the limit as n goes to infinity of the ratio equals to 0, right? The limit, so the ratio of the coefficients in your power series, they get arbitrarily small. That means your series would converge for every real number. So the radius of convergence is infinity. Finally, if we have the ratio of the coefficients in the power series get astronomically large, right? That means your series will diverge for every complex number. And so the radius of convergence is 0. There's no point where it converges except at the center of your power series. If Z equals Z naught, you'll have possibly convergence or divergence, right? Depending on what the A sub k terms would be. All right. So with that, I want to go over just one example on showing convergence or divergence of a series, right? Find the circle and radius of convergence of this series. Okay, so pause the video and I want you to work on this showing that the series converges or diverges, okay? Well, so hopefully you have worked on this example. Figuring out the circle and radius of convergence implies that this series converges at some points in the complex plane, right? So to show the circle and radius of convergence, we want to use the ratio test. The ratio test on the a sub k terms, which in this case is -1/k divided by k times 2 to the k, right? So k times 2 to the k. A sub k plus 1 divided by a sub k, which equals to the limit as k goes to infinity of, so in this case it would be k plus 1 times 2 to the k plus 1 over -1 to the k plus 1. Oh, oops. It's the reciprocal of the a sub k term. So you're multiplying a k plus 1 by the reciprocal of the a sub k term. So -1 to the k plus 1 over k plus 1 times 2 to the k plus 1. 1 times k times 2 to the k divided by -1 to the k power. All right. So right away, we have some terms that will cancel, right? So we'll have -1 to the k will cancel with, so -1 to the k times -1, right? So this will cancel here too. And this term will be 2 to the k times 2. So 2 to the k's will cancel. And since you're looking at the absolute value of a number, the negative signs will go away. And so this would equal to the limit as k goes to infinity of 1/2 times k over k plus 1. All right. And so this would equal to 1/2. So what this means is, in order to show convergence, right? So we know that that the L value is 1/2. So, and it's not 0. So the radius of convergence is 1 over L, 1 over 1/2, which is 2. So the radius of convergence is 2, and the circle of convergence is where the modulus of z minus 1 plus I is less than or equal to 2. Okay, is less than or equal to 2. So hopefully that made sense. Before you go, here are some problems to check comprehension. 280. $12, 14, 16, 18, 22, 26, 28. 30, 32, and 33. Okay. So for next time, I will give you an overview on Taylor series in the complex numbers. And this will happen if your function is analytic at I should say infinitely analytic on any point z naught in the complex plane, right? So if you have that, we can define an infinitely differentiable complex function, and it's in the form of a power series, and it will be analogous to Taylor series and Taylor series to what you've seen in Calc 2. So thank you all for watching, and I will see you next time.